Hello everyone, welcome to this live coding session. Today, before we start coding, let's think through the valid parenthesis problem. A structured thought process is essential for solving coding problem efficiently. So understanding the problem statement. We are given a string that consists of only characters, which would be open parenthesis, close parenthesis, open curly bracket and close curly bracket, open square bracket and close square bracket. Determine if the input string is valid. We need to determine whether S is valid, meaning each opening bracket must have a corresponding closing bracket of the same type, and brackets must be closed in the correct order. Every closing bracket must have a previously open matching bracket. And now recognizing patterns. Now let's analyze some examples to recognize patterns. Example 1. Every close open parenthesis is followed by a close parenthesis. If that happens, then it's going to be a valid statement. If we have a properly nested parentheses, then it's going to also return true. If we have an open parenthesis followed by a close square bracket, then we're going to return false because they're not matching. And here this is properly nested, so it should return true. Before diving into the implementation, let's consider some important constraints. So here, the length of S is between 1 and 10 to the 4th. This tells us that brute force approach might be inefficient, but we're going to try it anyways. The string consists only of parentheses, so there's no need to handle other characters. And a valid string is fully balanced, meaning all brackets are correctly nested. So edge cases to consider. Before coding, let's think about edge cases. Empty string should return true because that should be properly nested. There is no parentheses. Then we got single brackets, which in this case is going to be just this. If we have a single bracket, that will return false. Now, if we have an unmatched string or parenthesis, that would also return false. And then if we have a mismatch, as we saw before, that would also return false. Now that we logically thought through the problem, let's start coding the brute force approach first. Then we'll move on to the optimized stack-based solution. Okay, so let's see what the brute force looks like. So the previous length is going to be -1. The reason we're using -1 is the previous length will be explained in the next line. While length S does not equal previous length. So here, length will never be negative. And in order for us to be able to enter into this loop, we wanted to make it negative because that's the only possibility. If we had a positive number and the length was that same number, we wouldn't be able to enter the loop and we will get a false answer. Okay, so now the previous length, now we're going to assign it length. And now we're going to remove or replace. We're going to replace. If we have open and close parenthesis, we're going to replace it with the empty string. Now we're also going to replace, if we have open and close curly brackets, we're going to replace it with the empty string. And if we have the opening and closing square bracket, we're also going to replace that with the string, empty string. And what's happening here is that if we get the same length of S equaling 0, then we're going to return true. So just to summarize, we track the length of S before each iteration here. So we first checked if they were the same. If they're not, we get into the loop. Then we gave it the length of it. And the whole goal is for length to keep decreasing throughout the entire code, all the way till we decrease to 0. And that happens by us replacing the, let's give an example, the input. So let's say the input is this right here. Well, let's actually use this. Say this. So the input, let's say, is s equals this. So on the first iteration, we see that there is no open parenthesis here. So we're going to go to the next one. There's no open curly braces, but we do have open and close square brackets. So we're going to remove that. And when we remove that, originally, the previous length was 4. And then after removing it, now we have this. So we started off with this. We started off with the length being 4. And now that we remove 2, we have 2 remaining when we go back here. So length is going to be originally 2. Previously it was 4. And now we're going to assign the new length, and it's going to be 2 now. Now we're going again to replace the string. We see right off the bat open and closing parenthesis. And for the next iteration, we're going to remove the open and closing parenthesis. And we're going to go back up to the top, and it says length equals, and in this case it's 0, and the previous length is 2. So we're going to assign length to previous length, which will give us 0. There won't be anything to remove here because it's already an empty string. So then it's going to go back up, compare length s, which is 0. Previous length is 0. So now we're going to break out of this loop, and now we're going to go straight here and says is length s equal to 0. This will return true. When this returns true, it means that this is a valid parenthesis. Now, looking at the time complexity, this is what we're looking at. Each replace statement here has a worst case scenario of O(n) iterations. And since we remove 1 or 2 characters per step, the worst case each time is going to be O(n). And again, just showing the example we worked through before here. Let's say on the first iteration, we have here the square brackets. We're going to remove that. And the worst case, the reason this is O(n) is because the worst case scenario is that this is at the very end of the string. So on the next iteration, we know that it's going to be n minus 2, because as we see, we're removing 2 here. And then on the next iteration, we know it's going to be n minus 4 because we removed 2 more. And that leaves us with 0. And the original length of the string, as we saw, was 1, 2, 3, 4. And we ended up with 4. 4, 4, that would equal 0. 4 more. So now, in order for us to figure out what the runtime for this is, we're going to need to use a formula. And this formula is number of terms, and we divide it by 2, times first term plus last term. So S will equal the number of terms that we have is 1, 2, 3, right? So each time we're decreasing by 2. So based on that, we're going to use n divided by 2 because we're decreasing by 2 each time. And then we already have divided by 2 here. So we just put it there. And then next, we multiply first term, which is going to be O of n, and then we're going to, so let's put n instead, and then we're going to add it to the last term, which in this case is 4. So then to simplify, once we simplify this is going to be n divided by 4, and then we're going to multiply n plus 4. And when we cross multiply, we're going to get n divided by 4 and square divided by 4, and plus the 4's are going to cancel out because we got n4 and then we got the 4 here. So the 4's are going to cancel out, leaving me with n. And now when we find O complexity, what we always want to do is we want to remove any constants. So the only constant we have here is the 4. So that leaves us with n squared plus n. And then since we're finding the worst case scenario, worst case is that it runs in n squared. And that's the reason why the worst case scenario is n squared. So now let's see if I got the test cases. Okay, so the test cases ended up being correct. So this runs as it's supposed to. And now let's compare it against other codes. See how well it did. This is the worst case scenario, as I mentioned. It does take 31 milliseconds, and it only be 5% of the people that have tried this problem. So it's not very efficient, neither in time complexity or in space complexity. Because when we talk about space complexity, the reason why it's not efficient is because each time we're just saving a new string. We're creating a new string every single time that we delete a pair. So going back to the description, if we had this, each time we're creating a new string, which takes up additional memory because strings are, again, they're immutable. So this is a new string, and that's the reason the worst case scenario is O of n. And as I said, this is inefficient for large inputs. So let's move on to the optimized approach. So thinking through the optimized approach, key observation that we took away from when we were trying to solve this problem is that each opening bracket, as we can see, must be closed in the correct order. This suggests that we need to track the order in which they appear. And when a closing bracket appears, it must match the most recent unmatched opening bracket. This suggests a last in, first out structure, also known as LIFO. LIFO, last in, first out, means the most recent item added must be the first one removed. This is exactly how nested structures behave. And from this example, we recognize that a LIFO pattern, a stack data structure, is a great fit because we push opening bracket onto a stack. When we encounter a closing bracket, we check if it matches the last open bracket. And if it matches, we pop the stack. If it doesn't match or the stack is empty, it is invalid. So based on that, the way we're going to work with the optimized approach, we're going to iterate through S, and it's only going to happen once. So it's going to be O of n. We're going to use a stack to store open brackets. And if a closing bracket appears, check if it matches with the last open one. If the stack is empty at the end, the string is valid, similar to what we did for the brute force. So here's the code. We're going to use a stack. Then we're going to use a mapping. And this is going to be the closing bracket, closing parenthesis, matching it to the opening parenthesis. Then we got the closing curly braces, matching it to the opening curly braces. Then we got the close square bracket. And we're going to match it with the opening bracket. And now we have all the opening pairs and closing pairs matched. Closing, opening, closing, opening, closing, opening. So now we're going to do our for loop for char in S. And if char in mapping, what we're going to do is we're going to do the top element. Equals stack.pop. If stack else is going to be the hashtag or the number sign, the pound sign. If mapping char does not equal the top element, then we're going to return false because we don't have a matching bracket here. Else, if we do have a matching bracket, we're going to append it. We're going to append that char, which is going to be the open brackets. Now in this case, we're going to return, if the stack is empty, that will return false. So because of that, what we're going to do is we're going to put not stack, so it returns true. The stack is empty, therefore this is a valid nested parentheses. So just to explain what the code is doing, we're going to initialize an empty stack to store open brackets. Then here we're just creating a dictionary mapping, storing matching pairs. Here we're iterating through the string. If a closing bracket, we're going to check to the top of we're going to check the top of the stack. So in this case, if the stack is empty, we're going to pop. If it's empty, it's going to return false. So therefore, we're going to store the number, the pound sign here. It's not going to match the chart here. So therefore, the top element is going to return false. Now, when we go again, in the next iteration, and let's start with, let's use an example here. If the stack is empty, we already said, that it's going to be return a false. If the top element doesn't match, then it's going to be invalid. It's mentioned here. And otherwise, it's going to pop, meaning if there is something here, it's going to pop it. And if the opening bracket here, then we're going to push it onto the stack here, which would be the stack we created. All right, so let's go through the example. So we got the chart that we're going through, which is the S, which is what we got here. If chart, which is going to be, is it in the mapping? So now let's start off with this guy over here. Is this in the mapping? Yes. No, it isn't. And since it's not, we're going to go straight. Yes, the parenthesis that we first got here is in the chart. And then if the chart is in the mapping, which is not, because what we're looking for is the closing parenthesis, closing parenthesis, closing parenthesis. And what we're finding is that that's not the case. And since that's not the case, we're going to actually do the else which means that we need to return this over here. It was nested too far. So then we're going to append this opening bracket to the stack. So now let's create the stack. And here we're going to put this value here, which means that S, so we put it here. We're going to append it, stack append the chart. Then we got S here. And then it's going to say if top element, if char in mapping. So now we're going to go to the second one, which is going to be this guy over here. And we're going to say if char in mapping, which again, this is opening bracket. So therefore, we're not going to find it here because we're only looking for closed brackets. So again, it's going to return false. So then we're going to go to the stack and we're going to add another value to the stack. And that's going to be the opening bracket. So now we're going to go over again here, and it's going to go for char in S. And now we're here looking at the closed bracket. So if char in mapping, which it is, now we got the closing bracket, which is going to be right here. Then here it says if stack, which meaning if it's not empty, which is not, then stack.pop, which basically means now we're going to actually remove a value. So we did this guy. We checked here that it is in mapping. Now we looked at S already. Now we're looking at the stack. And we're going to pop this value, which is the last in, first out. So we popped it and we're going to assign it to top element. So now here we're looking at the chart, which we were tracking this over here. Does not equal, so mapping chart. So in reality, this guy, which is what we found, will return this. And that's how we index it, by putting map chart. So let's show this. So we got map chart. We put this value here. And that is going to return this value. And that's what we're comparing right now. So at this point, we're going to compare does not equal, which is the one that we popped, the top element. And the top element that we popped, that went from here, was this over here. If that was the case, it's going to return false. But as we can see, they do equal each other. So we're going to go back up to the loop. And now we're going to go to the stack here, the S. And when we go to the S, now we're here. We're looking at the close parenthesis. If char in mapping, we're going to go again, and we're going to find the closing parenthesis here. And again, if stack, meaning that the stack is not empty, then we're going to pop. And what are we going to pop? We're going to pop this guy. Let's see. Let's look at our stack. So we're going to pop our stack, which is going to be the open parenthesis, and we're going to assign it to top element. And this will be empty at this point. So we got an empty stack now. And now here we're going to go to mapping, as we did before. And now we're going to put the closing parenthesis. And now we're going to say does not equal. Actually, when we do that, that's going to return the opening parenthesis. So now we're going to do a comparison. Does the opening parenthesis, which is the mapping chart here, does that not equal the opening parenthesis again, which is what we pop, the top element? And as we can see, they do equal each other, so it's not going to return false. So now we're going to go again to for in chart. And the thing is, there is no chart, so we already emptied it out. So we already went to the end of the stack. So now we're going to end the loop since we already reached the end of the stack. And now here we're going to say, is the stack empty? The stack is empty, so that will return false. Then we put not, so true. Since the stack is empty, then it's going to show that this was properly nested. And this will return the this is a valid parenthesis. So let's see how the code works. Let's see if I don't have any errors. So mapping is here. And top element, is it misspelled? It is here. So we got top element, stack, stack. Stack is here, stack is there. All right, so let's try again. Okay, so we got false answer here, false answer here. So let's see if I messed up any part of the code. Okay, so we got the stack, the mapping. Let's see if I did anything wrong with it. So it's open parenthesis, close, close, open, close, open. So that's good. Then we got for char in S. Then if char in mapping, then we got top element equals stack dot pop. So let's pop here. Let's properly pop it. And if stack else this, which would be the pound sign, if mapping chart does not equal top element, and then return false, I'll stack append char, and then return our stack. So let's see now that's properly coded. Okay, so now we have a properly functioning function. As you can see, all the examples return the appropriate answer. And now let's see how it compares to other users. As you can see, it went from the very worst to running at 4 milliseconds. It beats 27%, so it could still be more efficient. But compared to brute force, this one actually does much better. So talking about the code, how it works, we initialized the stack, we mapped it, we went through the for loop, found it in the mapping, we popped the top element. If they matched, we went back to the loop, otherwise we return false. And if it was an opening parenthesis, we put it onto the stack. Once we went through the entire loop, we see if the stack was empty. If it was, then we ended up returning true as a way of saying this is a valid statement. A valid placement of parentheses. Now let's analyze the time complexity of this code. So we iterate only once and perform all one push and pop operation. And based on that, since there's a for loop, this is going to be O of n, meaning we're going to go through the entire string. So if we have this, this code is going to go through the entire string, O of n time, only once. And in regards to space complexity, in the worst case, all opening brackets and stack hold an element, meaning we're going to end up storing all the opening parentheses into the stack. And therefore the worst case is, or in the event actually that we don't have, let's say we had the worst case, this is going to be O of n, which is, let's say we only have opening parenthesis. That's why it's O of n. The entire length of the string is store, making it O of n. And then now comparing the two. So brute force would be O of n2 time, as explained in detail during the brute force time complexity. And space-wise, it can store an entire string each time it's replacing it, so therefore is O of n space. So it's not efficient. Now when we go to the optimized stack approach, this one is the most efficient, just because, again, you're only going through the string one time, so it's O of n. But the space is still the same as before, so there's no improvement there. So the only improvement is actually in the time complexity. And then key takeaway: understanding the problem first help in choosing the best approach. And recognizing pattern example makes it easier to identify the right data structure. Using a stack simplifies the problem and makes it efficient. Analyzing time complexity ensures our solution scales well for large inputs. And thinking about edge cases like close parentheses, for example, all close parentheses or all open close parentheses, also help us in identifying how to approach this problem. And that's it for this session. If you found this helpful, leave a comment or like, and I'll see you in the next happy coding.